very proud to say that I'm a friend of Petar Kokotovic. And even though he was not my PhD advisor, I think of myself as a student of Petar Kokotovic, because when I was doing my PhD thesis, I read his papers and knew of him from his papers even long before I met him. And he knows very well that I was referring to a lot of his papers in some of my early work. And it's been a very good relationship over the years. I've learned so much from him. Petar Kokotovic is a pillar of control theory worldwide. He's a very well-known person in the area of control theory and applications of control theory. Some very serious, important applications that he's done in power systems and axial flow compressor control and automotive control systems. He was one of the developers of the very early automotive control systems, working with Ford. So he's had a lot of relationships with corporations, General Electric Company, Ford Aerospace, United Technologies, and so on. He's a very distinguished control scientist, like I said. He had a distinguished career at the University of Illinois after coming to the United States from his native Yugoslavia. He was at the University of Illinois from 1996 through 1990, where he held the Granger Chair. And in 1991, he joined the University of California, Santa Barbara, where he is to this day. He was the director of the Center for Control Engineering and Computation until 2003 over there. He's co-authored 10 books and many articles contributing to sensitivity analysis, singular perturbation methods, robust adaptive and nonlinear control, and applications. He's a life fellow of the IEEE, a fellow of IFAC, the International Federation of Automatic Control, a member of the National Academy of Engineering of the United States. In 1983 and 1993, he received the outstanding IEEE Transactions on Automatic Control paper awards. He presented the 1991 Bode Prize Lecture. He was recognized with the 1990 IFAC Plaza Medal. He has awards that I hadn't even heard of before, but they're very prestigious and very impressive. The 1995 IEEE Control Systems Award.
You haven't heard of that.
The Richard Bellman Control Heritage Award. Though the one I hadn't heard of was the James Mulligan Junior Education Medal of the IEEE. And that's because a lot of us focus so much on research that we don't pay attention to the education side, but this is a person who has paid lots of attention to the education side of his career and supervised dozens of PhD students. I used to know the number, but I can't keep track of the count. And he was a supporter of the ISR in its early days in the NSF Review Committee for the ISR. And I could talk some more, but I think this will about it.
Yeah, and you must have noticed that he helped reverse time. So, which, you know, in my age, it's very good for you to happen, even if it's only for 6 years. But indeed, it is a great pleasure every time I come to Maryland. And because my sampling rate was not too high frequency, the changes I see over the last 30 years, or I should ask exactly whether it was 27, 28, or 30 years till today, are tremendous. This has become a center, at least one of two centers of control system science and everything. I see all the faces here who contributed to it, so I will not mention all of their names. And I was mentioned here as a supporter of what was the Center Now Institute. I want to even say that I was supporter in contrast or in spite of the fact that years before ERCs were formed, I was a great opponent of the whole idea. And so therefore when all these wonderful colleagues of mine organized the center here, I was expected to be a sharp critic of it, but I became a great admirer and supporter and expressed my opinion, and I'm so glad to see that this tradition, that is already tradition after all these years, has continued. I'm also very glad that in addition to these not so young faces, I see many young faces, so that gives me great pleasure to speak about a very old topic. Not only that the topic will be old, you will have sort of an old era technology for presentations. So remember, a word is worth 1,000 pictures or animations. I was going to talk more broadly about feedback, almost to come back to the topic of some 15 years ago, not 50, 15 years ago, lecture that I gave, Joy of Feedback, where Ian's work and some other work from Maryland was mentioned, the role of feedback in many different areas of science. But then, because of the personality and my whole tradition, I decided to still stick to something more specific than that. I would like to overview what happened with fundamental properties of feedback that were so clearly presented already in the fundamental book about feedback by Bode 60 years ago, and then followed on and off and became very active recently. You have a young expert that has broadened these topics to communications and so on. I'm of course talking about Nuna. And I have worked with a group of very young people. You see their names. They're all very young except for my old colleague David Main from Imperial College. It will be a little potpourri of things and also consistent with my own taste, because as Ian pointed out, I worked in nonlinear control, in singular perturbations and so on, but in fact, when I started working, I was so enthused about Bode's concept of sensitivity, and so that my first results were using Bode sensitivity functions some 50 years ago, and my sort of closing results, more recent time, will also have something to do with Bode. Is this visible?
Mm-hmm.
Except for the picture. Let's give Mr. Bode full view. I was very pleased to be his host when the University of Illinois gave him honorary doctorate sometime just 3-4 years before 1982, as you can see. And now let's go to the technical part. You see, the fundamental problems of feedback, they evolved. They were actually not even first introduced for control purpose. Bode himself at some point said, okay, now network theory, system theory, and control are going separate ways. By that he meant control has abandoned feedback. There was a period like this when we were all concentrated on Pontryagin's maximum principle and this kind of theory. But today, what I will be focused on are two Bode. Well, first of all, I'll be talking about a simple feedback loop, and then I will move to the nonlinear. So this L transfer function is the controller and plant transfer function. Just spend some time getting my notation. Sensitivity function is 1 over 1 plus L. What people like to call today complementary sensitivity is the transfer function Ts, L over S1 plus S. And the two famous Bode integral invariants are given here, one for the sensitivity, that is limited by the sum of poles, unstable poles, sum of unstable poles. So you cannot reduce the sensitivity below a certain limit which is defined by the unstable poles. I don't have time to talk about it, but it has beautiful interpretation also. But a richer and more interesting interpretation is if you concentrate on the tracking integral, I would say, and spend some time looking at this, because we will need it as we go along. It is not obvious what it means, but it certainly means the following: that to achieve ideal tracking, you would like T, ideal tracking of this signal. You would like T to be 1, because then Y would be R. But this says that in case you have unstable zeros, logarithm cannot be 0, that means T cannot be 1. So in the presence of unstable zeros, it is impossible to achieve ideal tracking. We cannot push T to become 1, or to put this log to be 0. It looks a bit awkward, log, and then d omega over omega squared, and yet a very simple, clear message that it is sum of 1 over z. So I want to demystify this relationship to show its simple interpretation, to therefore somehow explain the meaning of it, and then to ask the question, can we use a nonlinear controller to avoid this limit? And if not, then there must be a nonlinear counterpart to this limit. So the topic today is, what is the actual meaning of Bode's constraint, number one, and number two, what does it mean, if anything, in the nonlinear setting? So these are the questions stated, and the way they will be approached, is, of course, limited by the ability of the speaker. The speaker likes to deal with nonlinear systems, the speaker likes optimal control, and the speaker likes singular perturbations. This is myself. So I will have these three ingredients combined based on very good previous work, excellent previous work, which is listed here, which unfortunately we don't have time to review. So my outline will be as follows. I will review the linear results from that point of view, from the point of view from which I will then go to nonlinear world. So I will give an introductory example, minimum energy problem, cheap control, and so on. Then I will do a similar thing for the nonlinear. I will stop to give a big picture here. I'll stop to give a big picture here. And if the time allows, I will mention two new topics which are of last few years, and current, in fact, of general nonlinear tracking problem, and also a possibility to avoid it. It is nice to give broad brush review of something, but it's even nicer if we can join together and go through some equations and very specifically understand what is going on. Let's do an introductory example. Forgive me for sounding just as if you're in class, but why not? Fine. Let's do a simple example. Remember, I want to show what is the meaning of this Bode formula, and I will use optimal control, in particular cheap optimal control. I will first take an example that every classroom takes, which is a double integrator, but I will put an unstable zero here. So in other words, the transfer function is 1 minus 1 over zs divided by s squared. Or if I take 1 over z to be beta, it's 1 minus beta s squared. Now I will not bother you, I'll take with general signal, I'll just take r equals 1 because it's enough for me to illustrate what's happening. I will make the change of variables so that tracking becomes really regulation to 0, so it is just shifting x to x minus r. And I will then formulate the cheap control problem. I want to minimize this error, ideally, the best possible way. The best possible way is when I basically put no cost on control. To work without cost on control, this would create an awkward problem, actually, a very singular problem. If I immediately put this equals 0, then there will be really no optimization problem. So I will put a penalty with an epsilon squared here. Then I will let epsilon go to 0, and I will ask the question, what happens when with the limit of j epsilon, does there exist a j 0 epsilon? This is a classical result that will follow by Quackernack and Sivan, derived by some other methods, but I will derive it here by singular perturbation. Now, I am approaching Bode from a different point of view. Bode is all in frequency domain, but if I want to go into nonlinear systems, I have to switch to the time domain to basically the only methodology that will work for nonlinear systems. That's what we are doing now. And why are we doing optimal? Because in optimal, when this epsilon goes to 0, then it is the best possible performance. So if j 0 is not 0, there will be a reason why it is not 0. Normally, if I can achieve ideal thing, j 0 would be 0. Well, everybody knows the Riccati equation for it, but there is something in this equation that is worth paying attention to. There is this singularity 1 over epsilon squared. To remove that singularity, I seek the solution in this scaled form, put epsilons and so on. I proceed, so the solution is in this form, and obtain. It is not hard to see in this example how I obtain this result. In other words, these epsilons cancel with this epsilon, everything appears very nice. Up to order of epsilon, I obtain this result and obtain that the non-epsilon part is 2 beta here, epsilon, epsilon, epsilon here, beta here, and then some other terms. Which means that the actual cost is, as you know, this quadratic form, which in this case simply becomes b times psi 1 squared. But when I look what this is, when I look at this beta, beta is 1 over z. So basically what I obtained now, that the cost is 1 over z for this simple problem. That immediately smells like Bode, doesn't it? The limiting value of minimizing the error is 1 over z, like we would get in the Bode case. There is more that I want to achieve with this example. I want to see how I come back to the system and to interpret what is the limiting form of that system. So, when I come back to the system, this is a high gain system because my control is 1 over epsilon, linear control with 1 over epsilon gain. This means that the system has a 2 times scale property because it's singular perturbation part here. When I set epsilon equals 0, I take the slope part of this and I obtain the remaining system. There should be a change then from the algebraic. I eliminate C1 and I eliminate C2 and I obtain the C1 subsystem which we call zero dynamics. But these zero dynamics are no longer unstable. Remember, I told you that the zero was positive and it was unstable. Now the zero dynamics are stabilized and stabilized in a very characteristic manner. The pole of that, the eigenvalue of that system, which was here, was transferred here. The eigenvalues of the zero dynamic system are the zeros of the transfer function. So we have shown 2 things here, that there is a mirroring in stabilization of the zeros, and that there is the result which repeats the Bode result with j being 1 over z, therefore non-zero limit. And now we will investigate. We know that this is now irreducible, that this is the best possible performance index we can achieve, and we see the similarities. Now we will investigate in more general terms what happens. To do this, I have to remind you of another simple optimization problem. Interestingly, I haven't seen in the literature the annal of quite this problem solved in quite this way, although it's a textbook problem. But we will get some interesting insight from it. Now, this relationship of this minimum energy problem with Bode and so on will not be obvious until my next couple of slides. But bear with me and just consider this. I'm simply minimizing this performance index for this system, but I'm making this A anti-stable for simplicity. So all the eigenvalues of A are unstable, and I want to stabilize it with V, but just barely stabilize it. This is the limiting stabilization. I'm basically putting this penalty rho here, so small that just the mere fact of stability will do. So I'm not expending more control than needed. In the limit when rho tends to 0, I will only recognize the stabilizing solution, but basically this is a stabilizing solution with minimum energy. So when I write the Riccati equation for it, I obtain this equation, rho goes to 0, I obtain this equation. My feedback matrix by standard ways would look like this. This is the open loop, this is the closed loop matrix. Now I rewrite the same Riccati equation with AC instead of A0, and I want you just to compare this and this. You see, these are almost the same equations, except there is a minus here and there is a plus here. Now, from this, let's not go all the algebra. From this, I obtain P0AC equals minus A0 transpose P0. In other words, feedback matrix stabilized by feedback is minus P0 inverse A0 transpose P. This matrix has the same eigenvalues as this matrix but with minus signs. So this is the mirroring or Hamiltonian property which says that the least energy you need to stabilize a linear time invariant system, in this case I took it for simplicity to be each eigenvalue to be unstable, the least amount of control energy you need is if you place the eigenvalues in the mirror images of the eigenvalues of the unstable eigenvalues. Now this is a known fact and it was nicely displayed again in the work of Xu and Davison in connection again with the Bode T integral. So now we want to see why this appears and how in the Bode T integral. I have hopefully prepared you with an example so that I can now do the general problem, which will be the same as the example we did, second order example, except, of course, being general, there is some additional stuff we need to do. We need to return a little bit to the linear system and argue the following: that every linear system with change of variables and some feedback transformation can be represented in this form. Well, let me say that here I've taken every linear system of relative degree 1 because I'm taking B1 to be CV and I've taken it to be non-singular. Of course, similar work with similar results will be obtained with higher relative degrees but with more notation, so let's not worry about this. So, what is the meaning of this? This is the system output taken as the state variable, and then the remaining state variables are these. But it turns out these are the state variables of the zero dynamics. In other words, the eigenvalues of A0 are the zeros of the transfer function matrix. I will again select this to be antistable, and now will come the main result about interpreting the Bode limit. Let's say the preview of this result. Notice that this output, which is controlled here with U, this is our output that is supposed to accomplish tracking. This output appears as an input in the zero dynamics equation, as an input. So all we are saying now is this output is supposed to be tracking a signal. But if the zeros are unstable, this output is also needed as a control to stabilize the zeros. There are two contradictory requirements of the output. One is I command you to track a signal. The other is I want the system to be stable. And the only way the system will be stable if your output stabilizes it as a control variable. So basically the message will be the amount of the energy that this output needs to stabilize the unstable A0 matrix, that amount of energy is not available for tracking. So the meaning of the Bode limit is you have to subtract for what is available for tracking. From this, you have to subtract the minimum amount of energy needed to stabilize the zero dynamics, and both output is to serve as stabilizing control as well as to track a signal. And now we do the mathematics of it. I do not, of course, fully expect that you will follow every little detail of my little carpet of equations, but I will lead you to some. I want to say, just like in the previous example, the Riccati equation has this singularity 1 over epsilon squared. Like in the previous example, I put scaled things. I need an extra term here for accuracy. So only one of the Riccati submatrices is not of the order epsilon. So when I crank my singular perturbation machinery, put this in and so on, I can explicitly solve for P1, I can explicitly for P1, I can explicitly solve for P2. When I substitute these, I get the equation for P0. Note, this is the only non-epsilon term. I get the equation from P0, and lo and behold, this is the equation I recognize perfectly. This is just that equation from the previous slide, which was the equation for the minimum energy problem. It is not too far, and from even observing this in a handwritten slide, it is not too far to make the following key conclusion. There is a minimum energy problem, in this cheap control problem. Inside that problem, there is a minimum energy problem. And therefore, this minimum energy problem corresponds to something. To what? To stabilizing this A0 matrix. What is the A0 matrix? The A0 matrix is the matrix of unstable zero dynamics. That minimum energy problem is the one which will determine the cost, the best available cost. The best available cost is again something like this with this P0 in it. The system that is controlled with this contains these two parts. And when we substitute things, I will not go through every detail here, we then want to exactly derive the Bode formula from here. So again, I have to now rewrite the coordinates. I have the system which is made of these two, but then when I put epsilon 0, I have to solve from here. So here is what I'm doing, this solving. I'm solving for this so-called slow solution. So this is now the original state of zero dynamics, and now this is the equilibrium point for the zero dynamics under the input signal R, which I take it to be constant. So there is a little calculation here. So I come to evaluate this expression. This expression is here. I substitute this C here, and I get a pretty big matrix expression, but no panic needed. To calculate the trace of this matrix, everything goes very simply. And lo and behold, the trace of this matrix, which accounts for what the value of the performance index is, the trace of the matrix is exactly sum of 1 over zeros. So these are the zeros of the triple ABC, all of them assumed unstable. These zeros are the limiting value of this expression is the trace of the limiting value of this performance index. So what is the meaning of the Bode log T formula, which says sum of 1 over zi's? The answer is it is the energy needed for the output. In this case, the output is transferred into tracking error, for the output to stabilize the unstable zero dynamics. And it comes straightforwardly. Actually, I haven't committed. I just wanted a slide to represent basically all the calculations. So therefore, it is definitely not that difficult result to obtain. It is within a standard course of control. Maybe at some point we will include it in the standard course of control to just show the limits and Bode and so on. So what have I said now? I concluded that the meaning of Bode T formula is that perfect tracking is impossible when an amount of output energy must be used to stabilize the unstable zero dynamics. This amount is determined exactly by the minimum energy problem for the zero dynamics, considering the output to be the control variable. Question: is there a counterpart of the Bode result in nonlinear control? Well, since we know that the minimum energy problem is playing a very important role, let's first review the minimum energy problem for nonlinear systems. Now I think we have been conditioned with everything as far as the notation is concerned. Let's write a nonlinear system to be affine in control. Let this W be the control variable. I will keep the C psi as the state variable, which will be zero dynamics variable. I will disclose that this will become a system output that is to control with minimum energy to stabilize this. I will make this vector field, the drift vector field, totally unstable, or better to say antistable, which is to say in reverse time it would be globally asymptotically stable. That's to present the actual situation very clearly. Again, I will barely penalize the state so that the fact of stabilization is the only thing that my optimal control is to achieve. Okay, so it's a well-posed optimal control problem for which here is Hamilton-Jacobi equation. You need to spend a little time just recognizing this. There will be a product of these two vector fields transposed. This is, of course, the optimal value function I want to find. The optimal control is in the interesting LGV form, if you wish. Let's denote it by alpha 0. So this is closed form solution for the optimal, if you know the result of the optimal value function, V. And even without calculating V, again, this is something I haven't seen in the literature, even without calculating the optimal value function V0, I can come with a very interesting insight. I use optimal feedback control using this yet unknown optimal value function, but the feedback system is this, and this system is stabilized. So what is this system? Remember, this is anti-stable. So when I compare this, and I see a term here, so when I take this as a common factor, then I have F0 minus this term. But this is F0 minus this term. What's going on? What is going on is that this term equals to F0. So when I put this 2F0 here, I get F0 minus 2F0, so I get minus F0. Minus F0 is this mirrored, non-linearly mirrored F0. So I have this system which is stabilized, and it is stabilized with the minimum L2 energy, and it is stabilized with the minimum L2 energy, so F0 is mirrored by minus F0. If somebody has seen this, it's not, as you see, it's an obvious thing, 2 lines to the right, so it must be in some books. I haven't found it, but the insight is quite fascinating to me. That the minimum energy stabilization means flipping things over as if you're creating a system which is a reverse time property of your system. When you look at the Hamiltonian structure, you understand from the hyperbolic manifolds of the Hamiltonians that this is how it should be. And yet, for the purposes of feedback stabilization, I haven't seen this fact, so clearly for the nonlinear case exhibited as it is, and the derivation is very simple. What does this mean for the Bode equivalent in the nonlinear systems? Well, if you have followed even halfway of what I was saying about a linear system, you will not be surprised that the meaning will be structurally the same. Of course, nonlinear is nonlinear, not linear, but here is the nonlinear normal form. We'll talk in the Isidori language, Isidori versus language. So this is a normal form, relative degree 1. Basically, for this form, what I have, the control variable is controlling the output, and then the output is controlling the zero dynamics. This is not a general situation in nonlinear systems. This form doesn't always exist, but we'll ignore that complexity and we'll say, okay, at least this reasoning will be applied to situations where this form exists. Again, I defined a cheap control problem, and in case somebody was a bit sleepy when I started, I will repeat again, why is this cheap control problem related to the original problem of Bode? It is related because if this epsilon goes to 0, I'm putting no penalty on control. Therefore, if there is a solution that is the best in some sense, the solution that doesn't penalize control is the one. We will again get it in the limit. Now we have to deal with Hamilton-Jacobi equation, which is a much more complex object than the Riccati equation. I do not at this moment require that you remember anything other than that there is a definite place where the singularity due to this cheap parameter epsilon appears. The feedback control repeats that 1 over epsilon squared in feedback, therefore it will be a high gain feedback. And when we do this further work, we will mimic what we have done in the Riccati case in the following sense. We will seek the solution for the optimal value function simply as V0 plus epsilon V1 plus order of epsilon squared. This is an ansatz. This is what in asymptotic analysis you can also call a guess or an attempt, because there is no guarantee. This is not the Taylor series. There is no guarantee that, say, the first epsilon term will be epsilon. It could be epsilon squared, it could be square root of epsilon, it could be who knows what. So it is only, if you wish, a guess. But if I manage to prove that this works, then it's more than a guess. So we substitute this, and we get this result. Of course, this type of substitution, I get rid of 1 over epsilon here, I get order of epsilon here, but I want to recognize the terms. And why we have dealt with the minimum energy problem is because everybody in this room, in this wonderful audience, will have now to recognize that this has something to do with the minimum energy problem for the control variable for the output variable as the control variable. This is the problem we just solved on the previous line. And then there is something else here. So when we treat this, we will say, what if this optimal control alpha 0 derived for the minimum energy problem is now used to be substituted here? We cannot substitute it because this is a different problem. But we can at least use it in an expression that now contains the explicit difference between the solution of the minimum energy problem and y. And here is the key. Here is eta. And y, if y were the stabilizing control, not the output variable, y would have to use alpha 0 as the feedback law, and this would be 0. Y minus alpha 0 is an interesting variable eta. What does this variable mean? This variable means it is something that after this goes to 0, y then becomes the feedback control of the zero dynamics. And that feedback control is exactly the same as the feedback control from the minimum energy problem. You don't need to be an expert in singular perturbation entity. So everything is elementary here, and the fact that I had a pre-knowledge, or if you wish, a prejudice, that this problem will split itself into a minimum energy problem and something else, that prejudice led me to make this substitution. I make this substitution everywhere. You see, instead of y, I write eta plus alpha 0. So for now, treat it as my prejudice. And then I get this. So when I look at this, now I have a true minimum energy problem, and I say this would be Hamilton-Jacobi equation for this problem. This would be, this problem now has etas here. I'm minimizing this, not minimum energy, take it back. So this is a cheap control problem. When the minimum energy problem was separated, satisfied by alpha 0, this is what is left. This is what is left. And then when you look what this problem is, so once again, this is the minimum energy part. When I substitute this in the full equation, the minimum energy part drops out. And what is left? This plus etas. So this is what I get. And when you look what this is, beautiful in fact, it is this problem. It is this cheap control problem. It is this cheap control problem for this simple system. Look how simple this system is. There is U and vector field G. In this, C is considered as a constant, and this is the only variable. This here, C sits as a parameter. Sure, I have to solve it for every C, but nonetheless. So this is that variable that indeed can be forced to 0 rapidly. As a cheap control problem, the control will be high gain, and in fact, control will be just -1 or epsilon times this eta. So the true control does this. The true control rapidly eliminates, exponentially fast, the deviation between the feedback control needed to stabilize the zero dynamics and the leftover of the system. So the leftover is fast, and what remains slow keeps working to stabilize the zero dynamics. So the result then is this system here, which we know how to analyze. This is a singularly perturbed system. The fast part is deviation from this alpha 0. When the fast part disappears, when this part disappears, we are back with this perfectly stabilized zero dynamics and mirror imaged in the minimum energy sense. I will just do a couple of things about the singular perturbation analysis. You know, if it's a hobby, it's a hobby. You just cannot resist it. So that's what it is. But it's also to show that every step of the way we have exact results in the asymptotic sense. it may sound as contradiction, but no. Asymptotic analysis can be examined in its own way. So, the error between y and alpha 0 tends to 0 rapidly. This is a singular perturbation system. The limiting value of the performance index is V0, which is the solution of the minimum energy problem. So this is your Bode counterpart. Of course, when you deal with the nonlinear system, you have to study the stability. It turns out that the stability can be studied, if you wish, as expected, by using this piece of the optimal value function, and then also the quadratic, the L2 norm of this zeta. You write this, etc. So you prove asymptotic stability and all good things. And you see, quickly on an example, what really happens if you haven't seen in the general context. My example is as follows. Y dot equals minus 6c to the 5th plus u, and c dot c cubed plus y. So y is driving this system. This is already standard form. Hamilton-Jacobi equation here I can explicitly solve. I solve the minimum energy problem, and I obtain the feedback system in this form, and for this feedback system I obtain the actual value to be just 1 over 2 c to the 4 of the energy I must spend in order to stabilize the zero dynamics, and therefore this energy is not available for tracking. This energy is not available for tracking. What is the big picture? Just as I said already, that in the nonlinear counterpart of the Bode T formula, the Bode tracking obstacle, is the result of the nonlinear cheap optimal control problem, which requires that an amount of the output energy be used to stabilize the unstable zero dynamics. This amount is determined by a nonlinear minimum energy problem for the zero dynamic subsystem. Now, if I have another 5 minutes.
Sure. Perfect.
So far, these are the problems that are not the full generality. Then I had my wonderful young colleague, Joao España, and his postdoc, Pedro Aguiar, and Pedro essentially developed full general nonlinear tracking problem with exosystem and so on. Now this, if you are not informed of the, say, Francis solution of the tracking problem for linear systems with exosystem and Isidorian co-worker solution for the nonlinear systems, maybe this will not make that much sense, but I will try to still give some intuition. The exosystem is the system which generates the signal that you want to track. So this signal is R. So this is a nonlinear system. Its function is S, so it's a nonlinear system in W. There is an output function Q. This generates the R, and this nonlinear system is known. So you may think of this as follows. To this original system, you add a dynamical system that will generate the signal you want to track. So this means you will know the signal you want to track up to its initial conditions. You will not know initial conditions. So what is the meaning of the solution then to this problem? The meaning is, in some sense, an observer's problem. The only thing unknown that defines the signal to be tracked are the initial conditions here. In the full space of these variables x and w, a manifold can be defined, and the pi function defines this manifold. So the tracking will be occurring on this manifold. So for now, you just think that there is a function which defines the manifold, and to solve the tracking problem in this fully general sense, you have to find this manifold. The tracking is achieved when you're on the manifold. This is it, how much I want to say about this general thing. I will say that we know how to solve it, not for all nonlinear systems, but only for a class that we are quite comfortable with, which is this class with what we call backstepping structure. We take some changes of variables, and then we define, as you would expect, a combination of the cheap control problem and the minimum energy problem. So this part is the same as before, and then we prove what the limiting performance index is, and again the same thing holds, namely the limiting performance value is limited by the required energy to stabilize the unstable zero dynamics. Probably the best thing is if by the end of this talk we understand something that is happening in this example. Let's take this example. It's again a good nonlinear example. We have c minus c plus, just don't put any meaning to these variables. These are just state variables. C dot minus c plus c squared to 1, and then it's a third order system. It's two integrators and a system like this. So these will be zero dynamics again, and then the linear part is entering into nonlinear zero dynamics. The output is to 1 variables. Now, the signal we want to track, you can recognize as a periodic signal from here. Periodic signal from here, right? This generates basically a sinusoid. But this sinusoid could be non-linearly deformed, and then this sinusoid will generate this R. This particular manifold solution, when applied, etc., will create zero dynamics of this form. Zero dynamics will themselves depend on the manifold on which the tracking is to occur. They will be driven and eventually will have to be stabilized by the error. And the error, of course, is the difference between the signal to be tracked and the output. So this error drives this, and again, the meaning is that this error has to stabilize it if it is unstable. But now it's interesting. Whether this will be stable or unstable, it depends what signal you want to track. Because it's a nonlinear system, for some signals it may remain stable, for some signals it may be unstable. So in this case, it's clearly unstable when the signal has 2 pi 0 w minus 1 greater than 0. It is unstable for this case, and it's stable for the other case. So to illustrate this, Pedro has simulated two situations where only the magnitude of the signal to be tracked is changed, but this simply meant that we go from stable to unstable situation. And then we want to see two, if you wish, Bode-like limits in this case. When we follow the signal which allows the zero dynamics to be stable, we have only, in this performance index L2 known, we have only 10 to minus 6 order of the error, of the energy, the energy, 10 to minus 6. So it's not 0, but 10 to minus 6 for practical purposes, we can say it's 0. There is a very small error here if you look. And the tracking is almost perfect. Now we want to track a bigger signal which makes the zero dynamics unstable. So remember, this was 10 to minus 6. Here it is 1.2. So we have 10 to 5, 10 to 6 order of magnitude difference. The signal was just to be tracked was doubled in value. It doesn't mean that the zero dynamics are allowed to remain unstable. No, they will stabilize. The error peaks and then eventually goes to 0, but the energy needed to stabilize the zero dynamics is much bigger, 10 to the 5 at least. This is the action that is needed to stabilize the zero dynamics. So in conclusion, yes, there is a complete counterpart with the structural interpretation of the Bode classical limits in nonlinear systems for tracking of signals, for signal tracking. Well, we faced that, and which I will not talk about today, but we faced this and we then decided, okay, so clearly you cannot overcome these limits. If you cannot overcome the limits and you want to achieve bigger accuracy, you go back and ask yourself, is this really the problem I wanted to solve? And here, if I have a good group of control engineers, I would ask, how often has a control engineer been asked to solve a problem of tracking a time signal? I would bet once in 10 situations. It is almost never that we are asked to track a time signal. Suppose you have a robotic problem. You have pick and place. What you may be asked is to track a trajectory which avoids an obstacle. But you don't have to be told in advance with what speed to track. Even if you are given the total time needed for completing the task, it doesn't mean that the speed is prescribed. So in most cases, not to mention when we have vehicles and so on, in most cases, the tracking is really not a suitable problem formulation. We like to call it path following, and we are not the people who invented it. Robotics people have been doing it all the time. Ship navigation and steering people, the captains would not allow any signal. The captains say, let my ship be steered geometrically correct. I will determine the speed, how fast I want to go along. As long as I can have the solution to the problem with variable speed, but whatever speed I give, I still remain on the same geometric path. That is a natural problem statement for, I think, that we have in the control world. We have been, if you wish, indoctrinated by conditioned by our own history. And history is mostly filtering. Filtering experts were first to design servo systems for radars and so on. They have just transferred the time tracking of signals. And, you know, the good reproducibility, high fidelity of voice signal or whatever signal, which doesn't always, and in fact very rarely, fit the control problem. Now, the big question is, if I define instead of a tracking problem a path following problem, then what happens? At least one more variable pops out to be available as a control variable. If you allow me to modify the speed along a trajectory, sorry, see along a path, geometric path. If you allow me to modulate the speed, and every driver who needs to make a curve, right, will not try to reproduce a time signal. It will try to remain on the road and will modify the speed accordingly. So if you allow me to modify the speed, the question is, can I remove the Bode-like bounds, Bode-like limits in this new problem statement? What it amounts to physically, when we posed, España, Aguiar and I, and Dutch, when we posed this problem, we didn't really know what the answer would be. But we said, here, physically, is it crazy to think that if I'm driving a Volkswagen with a loose suitcase on top of it, on a figure-8 path, and in this case, the suitcase is the zero dynamics, unstable zero dynamics. Now, how many of you would now guess? Can I manipulate just the speed along this path to keep the suitcase from falling? It wasn't obvious, and we had several false starts. Well, since then, the proof is given. It will depend really on the curvatures of the path. The paths can be characterized, but for most common paths, circular and other paths, yes, you can modify the speed, taking the speed as the control variable, an additional control variable, and keep the suitcase on the top. So when I gave recently in China this example and worked it on, a student came and asked me, why don't you just use a piece of rope or magic cord and fix? I said, yes, this would be one way of stabilizing the zero dynamics, no question. And this would be just a good point to finish this talk.
Thank you very much. Fascinating presentation. I don't know if we have time for questions, but we'll take time for questions. Does anybody have any questions?
I want to see faces when they ask questions. I want light.
Okay, it's coming. I'm trying.
I press the wrong things. Where are the lights? Yeah, that's it. Questions? David?
Actually, I have another example.
I want questions from students first. I want it in the reverse order of age. Go ahead.
Phonograph records and needles. because you have to vary the speed sometimes. You're following the path of the record, not just tracking a time signal.
Yeah.
That's tracking. This is a path following.
Listen, path following, modular parameterization of the speed.